Jai Hind and welcome to all. Myself Shiwani Singhal from Applied Science and Humanities Department in Ajay Kumar Garg Engineering College will deliver a second lecture on this topic, spectroscopic technique and its application. In this lecture, I will discuss the concepts of UV visible spectroscopy and where electronic transitions and the terms which are used in this spectroscopy. And then in this lecture or in next lecture, I will discuss the Beers-Lambert's law and its numerical. And the references which I taken is from Y.R. Sharma book, Elementary Organic Spectroscopy, Shashi Chawla, and Industrial Methods of Chemical Analysis by B.K. Sharma. In previous lecture, which was L1, I gave the introduction of all four in spectroscopy. Now, in second lecture, that is in this lecture, I will discuss the overall concepts of UV visible spectroscopy. Now, the first is what is the principle and what is the range of this spectroscopy. As we know that the each energy levels, these are well quantized. Well quantized means for transition means whether it may be electronic, it may be vibrational or rotational. For each transition we required a fixed amount of energy. If the molecule absorb this amount of energy, or we can say if we irradiate the sample with this matching frequency or energy, then this energy get absorbed. Okay. For example, suppose I am bound to take 100 rupees note and somebody wants to give me 1000 rupee. So, I will not take the 500 rupees and 500 rupees because I am bound to take only 100 rupees. So, I will take the 10 notes of this 100 rupees to get this 100,000 rupees. The well quantized means the fixed amount of energy. Now, first is range. The range UV visible, and we know that visible 7 color spectrum and its range is about 400 to 800 nanometer, or we can say about 4000 to 8000 angstrom, and UV below this, so up to 200. So, if we take the extract range, so it is in between 200 to 800, but below 200 is termed as far UV region. So, the UV radiation range extends from 10 nanometer to 400 nanometer, and visible range it extends from 400 to 800 nanometer. But the range at which we discuss or find the UV visible spectroscopy is 200 to 800. So, far UV below 200. For far UV region spectroscopy is studied under vacuum condition because of absorption by oxygen and nitrogen. So, that is why in far UV region the detection is very difficult, and for detection we require vacuum instrument. The common solvent for preparing sample to be analyzed are either ethyl alcohol or hexane. We may take alcohol, we may take water, because they shows the absorption below 200, that is they are not absorbed by this UV visible. Now, next is so it is clear that the range is 200 to 800. Suppose suppose I want to calculate the energy at 200 nanometer. So, we know that energy E is equal to Hc upon lambda. Here we put the lambda 200 nanometer, but not in nanometer, we can write 200 into 10 to the power minus 9 meter or 7 centimeter. Planck constant is 6.626 into 10 to the power minus 34 joule second, and C is 3 into 10 to the power 10 meter per second. So, either keep all values in meter or in centimeter. So, unit should be same. So, by way through which we can calculate the energy associated with 200 nanometer. Now, in this valence electrons absorb the energy and thereby undergoes the transition from ground state to excited state. So, the next point is what is the ground and excited state. So, here to explain this, let us suppose this. These are the distribution of molecular orbitals, and basically what is the concept of this distribution? We know that initially the spins of electrons in molecular orbitals are paired and they are called ground singlet state or singlet ground state. So, initially at ground state spins are paired, but when the molecule absorb the UV visible spectroscopy, so the electrons they goes to higher state, and if the spins are paired then it is called excited singlet state, and if the spins are parallel they are called excited triplet state. Excited triplet state has lower energy, so we can say it is quite more stable. The reason behind this, it may be the electrons are comparatively farther apart, so there is no electron-electron repulsion. Generally, on absorption of UV visible spectroscopy, the transition from ground singlet state to excited triplet singlet state occur, that is with retention of spins. So, spin remains same. After the emission of energy, the electron may go from excited singlet state to excited triplet state, but directly ground singlet state to excited triplet state, this is not possible, or we can say this is symmetrically forbidden. So, simple we can say the orbitals of lower energy, these are basically highly occupied molecular orbital and these are termed as bonding molecular orbital. Energy of orbitals of excited state, these are least unoccupied molecular orbital. So, they are basically called antibonding molecular orbital. So, here the valence electron, they absorb the energy and goes from ground state to excited state, that is bonding to antibonding molecular orbital. And the next thing is, what is the other name of this spectroscopy? In this spectroscopy, we basically talk about the transition of electron, and that is why this spectroscopy is also known as electronic spectroscopy, because here we deal the excitation of electron from ground state to excited state, and that is why this energy is very useful to find the number of conjugation, to find the aromatic conjugation, to find the structure of conjugated or alpha beta conjugated compound or non conjugated compound. So, simple, here the basically the valence electron they goes or they absorb the energy and goes from ground state to excited state. The absorption is characteristic and depends on the nature of electrons present, and the absorption of light basically it depends which type of electrons are present. As we said that the orbital molecular orbitals, as we know that atomic orbitals will combine and form the molecular orbital, and these molecular orbitals are bonding as well as anti-bonding. So, the electrons in bonding molecular orbital they are basically are of three types. First is sigma electron, second is pi, and third is n. Sigma means there is no unsaturation, only this type of bonds are formed. Pi electrons, pi means unsaturation is there, means this type of bond, and n is termed as non-bonding electrons or non-bonded electrons. Now, before this, as we say that absorption occur, so in this spectroscopy we get the absorption spectra, and which type of absorption spectra occur? Here we find spectra in between absorbance, how much absorption occur at which wavelength. So, at y axis we took the absorbance and at x axis we took the wavelength, and suppose wavelength is initially we took 200 and then 300. This is the increasing order of wavelength, as we know that energy is inversely proportional to wavelength. So, this is the decreasing order of energy. So, basically the curve starts from here because lower energy to higher energy. So, here we find the absorption spectra like this, and at this value the absorption is maximum, and this value of lambda is termed as lambda max. So, as the electronic energy levels are quantized means they have fixed amount of energy. If the molecule has or radiation has sufficient energy, then transition occur, otherwise no transition will take place. Discrete line should appear in spectra for every transition, but in this spectroscopy we do not get discrete line, we get a broad spectrum. The reason behind this, the electronic spectra or electronic transition is also associated or accompanied by vibrational as well as rotational spectros transition, and which leads to a broad band instead of discrete line. I have already discussed this type of molecular level distribution, and here it is clear that electronic excited state, it is associated with vibrational energy level, and vibrational energy level are also associated with group of rotational energy level. So, if there is a slight transition in electronic state, so there may be a transition in between vibrational as well as rotational energy state, and that is why we get a broad spectrum. And in this is the absorption, and in absorption or in a UV visible spectra or absorption spectra, we took the absorbance versus wavelength, and where the maximum value of absorption occur, this value is termed as lambda max. Now, types of electrons involved in UV visible spectroscopy. I think it is clear that simple, initially the lower energy bonding molecular orbital and at higher energy anti-bonding molecular, and lower energy levels are HOMO, that is highly occupied molecular orbitals, and higher energy levels they are LUMO, that is least unoccupied molecular orbital. So, initially there are 3 electrons, sigma, pi and n. Sigma, I think I have explained this. These electrons are involved in saturated compounds, that is no double bond, no triple bond, and the amount of energy required to excite the sigma electrons are high, because it is the in lowest level. Sigma electrons do not absorb near UV region, but absorbed in far UV region, and this point I will discuss in transition. Pi electrons mean unsaturated, and it may be trines or aromatic compounds. N is involved in bonding between atoms in molecules, so it is called non-bonding electron. For example, organic compounds having nitrogen, oxygen or halogens. Now, this is the transition point, and if it is not clear, I will make this. This. So, lower sigma, pi and n, which is bonding. At higher level, pi star and n star, sigma star, which is anti-bonding. These two least LUMO and these 3 HOMO. Energy absorbed in UV region by valence electrons cause transition from ground to excited state, and the energy required for various transitions, they have following order. How basically? The first transition, sigma to sigma star. Sigma, this HOMO, sigma star. So, the transition from sigma to sigma star is possible symmetrically as well as energetically, but this transition require highest energy. highest energy means lowest wavelength. Lowest wavelength means far UV region, and in far UV region the detection is difficult because of absorption by oxygen and nitrogen. So, first transition, which is sigma to sigma star, this transition is energetically forbidden because of in far UV region, and if we want, so we have to take what vacuum instrument. That clear? So, sigma electron is excited from corresponding antibonding orbital, and its energy is about, or energy required is about 150 nanometer, which is comparatively very, if we find the energy as compared to wavelength, it is high and it comes in far UV region. And in which type of molecule this type of transition appear? Saturated compound, for example, C2H6. In ethane, there is no heteroatom, so no n electron. There is no double bond, unsaturation, so there is no pi electron. So, in this case only sigma electrons are there. It means if the transition occur in this molecule, it will be only sigma to sigma star. So, this line I think it is clear, it is observed in saturated compound. Now, second transition, few points are also there. In methane there is no unsaturation, no n, so it undergoes and sigma to sigma star transition, and absorption occur at 122 nanometer, which is below 150 nanometer. Okay. And this region is quite less informative. And I think this point is also clear. The excitation occur with net retention of electronic spin, that is singlet ground state to singlet triplet, singlet excited state. Now, second transition is pi to pi star. Pi to pi star means if unsaturation is there, for example, butadiene CH2 double bond CH, single bond CH, double bond CH2. In this butadiene there is no heteroatom, that is no n electron, but double bond is there. Double bond is there means pi electron is there. So, in this molecule which type of transition is possible? Pi to pi star, and we know that pi bond is always formed after the sigma bond. So, there may be sigma to sigma star. So, pi electron in a bonding molecular orbital is excited to corresponding anti-bonding molecular orbital, which is pi star. In this case, pi to pi star, that is pi to pi star, this pi to pi star. And first transition, it was sigma to sigma star, this maximum. The energy required is less as compared to n to sigma star. We find this. The compounds containing multiple bonds without heteroatom, they undergo pi to pi star transition, and the energy, it is corresponding to 200 nanometer. This is wavelength, and when we find the energy by E is equal to Hc upon lambda, we can find energy. Absorption usually occurs in ordinary UV spectrophotometer. Absorption band in unconjugated alkenes, absorption band in carbonyls. In case of carbonyl, suppose there is double bond means pi is there. So, there may be a possibility of pi to pi star transition. Now, third is n to sigma star. N to sigma star, if we visualize this is n. So, n to sigma star, and these are highly occupied and these are least unoccupied. So, n to sigma star is this third point. So, in this case, which type of molecule generally shows? The compound having heteroatom with unshared pair of electron like oxygen, nitrogen, sulfur. For example, methyl chloride, CH3Cl. Now, in this case, there is no pi bond, so no pi transition, but Cl has non-bonding electron, that is lone pair of electron. So, in this case, there is a possibility of N2 sigma star, and we may write, it is your choice, N2 sigma to sigma star. Sigma to sigma star is not compulsory because it is energetically forbidden. So, if you want to write it, otherwise not, but this type N2 sigma star is important. This transition requires less energy than sigma to sigma star. Obviously, sigma to sigma star has maximum. So, second is N2 sigma star. Third point is important. In saturated alkyl halides, suppose CH3Cl and CH3I, both are halogen, but electronegativity decreases. The energy required for transition decreases with increase in size or decrease in electronegativity. Means methyl chloride, it shows a lambda max at 173 nanometer, while methyl iodide, it shows a lambda max at 258 nanometer. Means in this case, if we compare the electronegativity and electronegativity decreases, the lambda max it get increased, or we can say if the size increases, it get increased. Now, next point is, this type of transition is very sensitive to hydrogen bonding. For example, in alcohol and amines, they are capable to form hydrogen bond with solvent, that for like water, because of presence of non-bonding electrons in oxygen or nitrogen, and which require comparatively higher energy. And that is why hydrogen bonding, it shifts the UV visible absorption towards shorter wavelength, because it required higher energy, and higher energy means lower wavelength. Okay. Now, fourth transition is N2 pi star transition, and which generally it required more than 200 nanometer. So, in visible range, this type of transition occur, and as we know that suppose some material, it looks green, it means when we pass the white light, which is a combination of 7 color, and it absorbs the red color and its complementary color is green, and due to this transition the thing looks green. It means the color basically which is shown by naked eye, it is due to, it may be due to this transition N2 pi star, and there are some other reason like ligand metal transition, DD transition, or etc. So, an electron from non-bonding orbital is promoted or is excited to antibonding pi star orbital, and this type of transition occur where the double bond appear with heteroatom, and this transition required minimum energy. Minimum energy means highest wavelength and highest, and if we compare 200, 400 and 800, the higher wavelength appear in visible region. So, we can say this type of transition or this type of absorption occur in visible region. So, if we summarize all type of transitions, it will let this is sigma, pi, and this is non-bonding, and higher energy antibonding like this, this. So, if we compare all 4 transitions possible in a molecule when we pass ultraviolet or visible radiation, then first transition it was sigma to sigma star, and second n to sigma star, third pi to pi star, and fourth n to pi star. So, all these 4 transitions are possible or allowed. Other transitions are also there like sigma to pi star, pi to sigma star, but these transitions are symmetrically forbidden. And if we compare the energies of all 4 transitions, sigma to sigma star, it requires higher energy, highest energy. So, that is why occurs in far UV region, then n to sigma star, and then pi to pi star, and for n to pi star least energy is required. And that is why for this transition we can say that since the minimum energy are required, so generally this transition appear or occur in visible region. And suppose examiner ask, find the transition in CH3 CN like this, find the transition in CH3NO2, suppose this, and find the transition in acid CH3COOH, all possible transitions. Now, in this case CH3C triple bond N, in this case unsaturation is there and nitrogen has unsaturated or unpaired electron, that is non-bonding electron. So, in this case pi is there, N is there. So, possible transitions are these all 4, that is sigma to pi, N to pi star, pi to pi star, N to sigma star, and sigma to sigma star is there. Now, again N double bond O2, same situation is there. Here pi bond is there, non-bonded electron is there. So, all 4 transitions are possible. Suppose in amine, that is in CH3NH2. Now, here non-bonding electron is there, but there is no unsaturation. So, in this case the transitions will be only N to sigma star or sigma to sigma star. CH3COOH, in acid CH3COOH, C double bond O. So, double bond is there, oxygen is heteroatom which has non-bonding electron. So, in acid all 4 transitions are possible. So, these are the 4 transitions which may possible in a molecule, and these 3 are of lower energy. So, bonding, these 2 are higher. So, anti-bonding, these here H highly occupied molecular orbital, and these are lower unoccupied molecular orbital. Now, next is there are 2 terms which are used in UV visible spectroscopy. The first term is chromophore. It is a Greek word and the meaning is color carrier, and we know that in those compounds which absorb ultraviolet visible radiation, they appear colored, and the color intensity or color, it depends on the wavelength of light. So, they are defined as nucleus of any isolated covalently bonded group responsible for absorption of light radiation. Any group which shows absorption of electromagnetic radiation in UV visible region like C double bond C, C double bond O, NO2, etc., they are termed as chromophore. So, chromophore means or we classified the chromophore in 2 categories. First, those have pi electron, means where the pi to pi star transition is possible, like ethylene CH2 double bond CH2, like acetylene CH triple bond CH. And second category is those have non-bonding electron with unsaturation. So, here the possible transition is N to pi star, like NO2, like carbonyl group, like CN or etc. So, basically we can classify in these 2 types. So, some of the important chromophores, they are carbonyls, acids, esters or etc. So, I think it is clear those type of group or compound which shows a characteristic absorption band or which develop the color, they are termed as chromophore. Now, next is oxochrome. Oxochrome is totally different. They are not color developing group, but they increase the intensity of color, means they are saturated or unsaturated group which themselves do not absorb radiation, do not show absorption maxima, but whose presence shift the absorption maxima or enhance the intensity or absorbing property of the chromophore. For example, just like suppose catalyst. Catalysts are those compound which increase the rate of reaction, but if we increase the promoter or poison, then the rate get decrease or increase. So, oxochrome is like a promoter or poison and chromophore is like a catalyst. So, they are also known as color enhancing group. All oxochrome, they have one or more non-bonding pair of electrons, and oxochromes are basically introduction of any group like NH2, OH, OR or etc. For example, azo group. Azo group is like benzene ring suppose, and then N double bond N, and suppose this is. We know that this azo group, it shows, it impart the color in dye. So, since it it's a color developing group, so it is called chromophore. But if we introduce OH group at this side, the brightness or intensity of color increases, that is the OH is the oxochrome. It extends the conjugation of chromophore by sharing the non-bonding electron. For example, benzene. Benzene shows absorption maxima, that is lambda max at 255 millimicron or nanometer, and its epsilon is 203. But in case of aniline, its lambda max, it become 280 nanometer. It means when we introduce NH2 group in benzene, its lambda max increases, that is aniline, that is NH2 group, it is oxochrome, and because it increase the intensity basically relate with the epsilon. So, it increase the intensity as well as lambda max value. And chromophore, when we introduce the chromophore, the lambda max also get increase. And basically I finished this lecture here, and next means absorption shifting or transition intensity shifting I will discuss in next lecture. Thank you.